reverse it, converse statements. I think these are super cool logic statements, and I really enjoyed this lesson. So in chapter 1, you learn to write conditional statements to express geometric relationships, like if angles are vertical angles, then they are congruent. But what happens if you reverse a statement? Will it still be true? In this lesson, you will investigate what happens when you reverse a conditional statement. Again, those if-then statements. So hopefully we have that. We're going to definitely, I think, want to make sure that we know what the conditional statements are from in chapter 1, but also the converse statement is when we swap the if and the then. So if a conditional statement, in a conditional statement, the if portion of the statement is called the hypothesis, and the then portion is called the conclusion. If you reverse the order of the hypothesis and conclusion, then you've created the converse of the statement. So write the converse of the conditional statement. If angles are vertical angles, then they are congruent. So the converse, again, essentially is really as easy, and sometimes the language doesn't make a lot of sense, but you switch the if and the then. So it literally is like this simple, but like I said, then you might want to clean up some of the diction of it so it sounds better. So you wouldn't say if they are congruent, but you'd maybe say if angles are congruent, then they are vertical. That would be the converse statement. We switch the if and the then of that original statement. So you can see that we switch the if and the then. Now it says, is the original statement true? If angles are vertical angles, then they're congruent. Is that true? Well, if angles are vertical, right? If we go here and we say, hey, look, these angles are vertical, they're congruent, I would say that's true. Now, is the converse true? If angles are congruent, then they're vertical. Well, these are congruent angles. They're corresponding, and they're not vertical. So I would say, no, those aren't always true. So here, the original statement is going to be true always, but the converse statement isn't always true. Again, we can think of other angles. We can think of other angles that are congruent that are not vertical, right? So if the angles are congruent, they might be corresponding, they might be alternate interior, they're not necessarily vertical. It says every conditional statement has a converse. Consider the arrow diagram for a familiar relationship below. A triangle is congruent, all pairs of corresponding sides are congruent. Again, this becomes really like an if-then statement, right? It's just these arrow diagram statements are conditional statements without the if and the then. So it says in math, to say that a statement is true, it must always be true. That is, it must follow from a definition or a theorem. Is the arrow diagram true? If triangles are congruent, then all pairs of corresponding sides are congruent. I would say, yeah, that's always true. Yes, it's true. If the triangles are the same size, that means the sides are the same sides as well. So write the converse in this arrow diagram. So again, we'll sort of just switch it. We'll say, and again, maybe I'll type this, all pairs of corresponding sides are congruent. Then we have an arrow, right? We can kind of go up here and make an arrow. And then we will say triangles are congruent. That would be our converse statement there. Now it says, is this statement true? If all the sides, right? I'd say, yeah, this is true as well, right? If the triangles are congruent, then the sides are congruent. But if the sides are congruent, we have side, 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 triangle congruence, and we can say the triangles are congruent. So is this statement true? We would say yes. Oh, I need to get rid of my arrows there. Yes, that's true as well. So sometimes the counterexample is false, but sometimes the counterexample is, sometimes the converse statement is false, but sometimes the converse statement is true. All right, so it says, let me pause for a second. I think I screwed something up. I answered B was both parts of this. Is the converse true? I thought it was saying C was true, so my mistake. Now it's saying consider this statement. Is this statement true? If triangles are congruent, all pairs of corresponding angles are congruent. Yeah, that's also true. Now it says write its converse. Is the converse true? Well, let's write this converse first of all with a little arrow before I forget. Now let's go ahead and let's type this up. We're going to say all pairs of corresponding angles are congruent. That went real well. Whatever, I'm just going to put another arrow. I don't know. There. My bad. I shouldn't have put the arrow first. That was dumb of me. Then we're going to say the triangles are congruent. Well, let me ask you something. Up here we had side, side, side is triangle congruence. Do we have one that says angle, angle, angle is triangle congruence? So I would say no. I would say the counterexample is not always true. So let's go ahead and change this. We'll say not always true. My goodness. Not always true. I'm having trouble keeping track of these questions. They're coming in too hot and heavy. All right, so it says write the converse of the arrow diagram below. Is the converse true? Justify your statement. So, I mean, I think the first thing we should do is decide if this is true. If a polygon is a rectangle, the area is the base times the height. I will say that is true. Then I'll write the converse of it. The converse would say the area of a polygon is base times height, and we'll essentially say that means the polygon is a rectangle. All right, so is that always true? Can we think of any other shape that is base times height besides for a rectangle? And I think that there are some. Let me pause for a second and go with it. I know some are like the average of it. Obviously a square I think would be base times height, but I don't know if you would consider the base times height separate, so I'm trying to think of something that's different, so let me see. All right, well, I didn't think of it on the spot, but a parallelogram would be a shape that is base times height. And again, a parallelogram is essentially just a squish square, right? I'm sorry, a squish rectangle, so something that looks like that. So we would just say the base times the height would give us that as well. So yeah, we'll say the converse is false here. All right, so, and again, we only need one counterexample to prove it's false. So let me go ahead and show you one of my absolute favorite ones before we, actually, let's do these ones first. Let me do my favorite one first, and then we'll jump into this. So here's my favorite counterexample, which really has not a lot to do with math, but it does have a lot to do with logic, I think, and I think it's kind of interesting how often this one is missed by very intelligent people. So here we're going to have our statement. If there is life on a planet, then the planet can support life. Now, if you think about this in terms of like not just an astronaut jumping on the moon, but like actually like if there's life living on a planet or whatever, then the planet can support life. Well, this is true, right? There wouldn't be life on the planet if the planet couldn't support it. But let's write the converse. If a planet can support life, then there is life on a planet. Well, think about the Earth. What if nothing was alive on the Earth? Can you imagine that? I can, right? You got the ocean, you got rocks, but nothing alive. But it's the same Earth, just everything isn't alive on it. but it could support life. It just doesn't because there's no life on it. So the converse is actually false here, which is kind of interesting. So the next time you're around people who say, look at in the stars, there's a million planets, more than a million planets, there's infinite planets, and on one of them there has to be life. Well, that's actually not really true. It's possible, and I'm not saying that it's not true. My point is it fails logic. You can imagine, again, if there's life living on a planet, then the planet can support life. That's true, undeniably. However, you can imagine a planet that can support life where there is no life on that planet, which means that the converse is false in that case. So I always think that's kind of a fun one. Kids don't always agree, but whatever. It's my video. If you don't like it, fast forward it. But I guess I don't care. All right, so here we go. For each statement below, rewrite it as a conditional statement or as an arrow diagram and state whether it is true or false. Then write the converse of the statement and tell whether it is true or false. So we're going to basically say, if a polygon is a square, then it is a rhombus. Would that be true or false? Well, what does it mean to be a rhombus? You have to have the sides being the same length. And I think that's about it. And that's true, right? A square is a rhombus. However, if I write the converse of this, and the converse would be if a polygon is a rhombus, then it is a square. Well, that's false, right? I mean, I hope we're all okay with the idea there that a square has to have right angles, whereas a rhombus doesn't. So the fact that a square has right angles doesn't stop it from being a rhombus, but the fact that a rhombus might not have right angles does stop it from being a square. So here we'll say the statement is true, but the converse statement is false. All right, next one. I'm kind of running out of room here. So every isosceles triangle is equilateral. So if a triangle is isosceles, then it is equilateral. God, I hate this one. So in my mind, isosceles means that only two sides are the same. I think some people argue that isosceles means that three sides could be the same. But the bottom line is, if a triangle is isosceles and two sides are the same, then it's equilateral. I'll say that that's false. The converse of that would be if a triangle is equilateral, then it is isosceles. Now, like I said, I think different people would argue different things here. I'm just going to go ahead and argue and say it's true that if three sides are the same, that means at least two sides are the same. So I'm going to go with true there. As a matter of fact, I'm going to go to the key here and let's look at 225b to see what answer the book thinks is true. If isosceles, then it's equilateral is false. Answers vary. If a triangle is equilateral, then it's isosceles, true. If a triangle has three sides of equal length, then it will always have two sides equal length. So it says see suggested lists and activities for further interpretations. So I think what we'll do here is we'll see for part B, the converse is true if isosceles triangles are defined as having at least two sides of equal length, which is a definition used in this course. The definition is called the inclusive definition. If a student uses the exclusive definition that an isosceles triangle must have exactly two sides, then the converse would be false. So thanks, book, for putting us in a position where it could be true or it could be false. I'm going to go with the one where it is true, but if you're arguing the opposite, I mean, you have a legitimate argument. All right, so the next one, two parallel lines cut by a transversal form same side interior angles that are supplementary. So if two parallel lines are cut by a transversal, then same side interior angles are supplementary. Well, I would say that that's true. I think we learned that in the last chapter, right? If you have parallel lines that are cut by a transversal, then the same side interior angles are supplementary. So let's go ahead and change that. if same side interior angles are supplementary, then two lines are parallel. And again, I'll say, well, geez, if the same side interior angles are supplementary, then yeah, probably those lines are parallel as well. So hopefully we understand the idea of a conditional statement and the converse. Hopefully we understand what a counterexample is, just something that disproves it. I would say that this lesson is pretty mucky. The book did a good job of making sure that some questions had multiple answers, which kind of made it a little bit more difficult. Anyway, that is lesson 213.